Hello. Hello and welcome to this video. In this video, we will go through Codecs, the second part which we have left. So we will continue the read through, and this would be probably last boring video for a long time because we have quite a bit of interesting stuff coming: date time, zone info, calendar, collections, ABC. So lots of data structures are coming. We have numerical and mathematical methods of that, functional programming methods, file objects, data systems, compression archiving, file formats, cryptographic services, and all that. So I think I had a temptation to skip this part because it is quite boring theory. So let's push through this to finish it, and then we can move on to interesting stuff. So we had read till incremental encoding and decoding, and we'll continue with this. The incremental encoder and incremental decoder classes provide the basic interface for incremental encoding and decoding. Encoding or decoding the input is done with one call to the stateless encoder or decoder function, but with multiple calls to encode or decode method of the incremental encoder or decoder. The incremental encoder or decoder keeps track of the encoding decoding process during method calls. The joined output of calls to the encode or decode method is the same as if all the single inputs were joined into one, and this input was encoded or decoded with the stateless encoder or decoder. The incremental encoder objects. The incremental encoder class is used for encoding an input in multiple steps. It defines the following methods which every incremental encoder must define in order to be compatible with the Python codec registry. So the first class is incremental encoder. It is the constructor for incremental encoder instance. An incremental encoder must provide this constructor interface. They are free to add additional keyword arguments, but only the ones defined here are used by the Python codec registry. The incremental encoder may implement different error handling schemes by providing the errors keyword argument. So we have seen the error handlers already. The errors argument will be assigned to an attribute of the same name. Assigning to this attribute makes it possible to switch between different error handling strategies during the lifetime of the incremental encoder object. The first method is encode. Encodes object, which is an argument, taking the current state of the encoder into account, and returns the resulting encoded object. If this is the last call to encode, final must be true. The default is false. Reset. Reset the encoder to the initial state. The output is discarded. Call.encode object final.true by passing an empty byte or text string if necessary to reset the encoder and to get the output. Get state. Return the current state of the encoder, which must be an integer. The implementation should make sure that 0 is the most common state. States that are more complicated than integers can be converted to an integer by marshalling or pickling the state and encoding the bytes of the resulting string into an integer. Set state, which takes an argument state, sets the state of the encoder. State must be an encoder state returned by get state. Similarly, we have an incremental decoder class is used for decoding an input in multiple steps. It defines the following methods which every incremental decoder must define in order to be compatible with Python codec registry. The constructor name is incremental decoder construct. So all incremental decoder must provide this constructor interface. They are free to add additional keyword argument, but only the ones defined here are used by the Python codec registry. It is the similar description as the encoder. Not much difference here. Similarly, we have decode. Decode will be similar, and state and reset and get state and set state are basically same description as encoder. Then we have stream encoding and decoding. The stream writer and stream reader classes provide generic working interfaces which can be used to implement new encoding submodules very easily. See encodings.utf_8 for an example of how this is done. Stream writer objects. The stream writer class is a subclass of codec and defines the following method which every stream writer must define in order to be compatible with the Python codec like stream. The constructor is stream writer takes a stream LRC is checked. All stream writers must provide this constructor interface. They are free to add. So it is the same thing as incremental encoder and decoder. The stream argument must be a file-like object open for writing text or binary data as appropriate for the specific codec. The stream writer may implement different error handlings, just like encoder decoders. The error argument is also similar to encoder decoder. Then we have write, which takes an object, writes the objects contains encoded to the stream, write lines, which takes a list, writes the concatenated iterable of strings to the stream, possibly by reusing write method. Infinite or very large iterables are not supported. The standard bytes to bytes codecs do not support this method. Then we have reset, which resets the codec buffers used for keeping internal state. Calling this method should ensure that the data on the output is on the clean state that allows appending of new fresh data without having to rescan the whole stream to recover state. In addition to the above methods, the stream writer must also inherit all other methods and attributes from the underlying stream. The stream reader objects is a subclass of codec just like writer, and it also takes a stream argument. So the description is quite similar to the writer. So you can have that. There is no need to reread that. Then we have read. The arguments are size is equal to -1, default arguments, cache is equal to -1, first line is equal to false. It decodes data from the stream and returns the resulting object. The cache argument indicates the number of encoded code points or bytes to return. The read method will never return more data than requested, but it might return less if there is not enough available. The size argument indicates the approximate maximum number of encoded bytes or code points to read for decoding. The decoder can modify this setting as appropriate. The default value -1 indicates to read and decode as much as possible. This parameter is intended to prevent having to decode huge files in one step. The first line in flag indicates that it will be sufficient to only return the first line if there are decoding errors on later lines. The method should use a greedy read strategy, meaning that it should read as much data as is allowed within the definition of encoding and the given size. Example, if optional encoding endings of state markers are available on the stream, these should be read too. Then we have read line, and the default arguments are size is equal to none, keepends is equal to true. It reads one line from the input stream and returns the encoded data. Size if given is passed as size argument to the stream's read method. If keepends is false, line endings will be stripped from the lines return. Then we have read lines, which takes two arguments, size int with default value none and keepends as true. It reads all lines available on the input stream and returns them as a list of lines. Line endings are implemented using the Codecs decode method and are included in the list entry if keepends is true. Size int is if given is passed to the size argument to the stream's read method. Then we have reset, which is similar to other reset methods. Then we have stream read writer objects. It is a convenience class that allows wrapping streams which work in both read and write modes. The design is such that one can use the factory functions returned by the lookup function to construct their instance. We have the constructor stream read writer, which takes stream, reader, writer, and other arguments. Creates the stream reader writer instance. Stream must be a file-like object. Reader and writer must be factory functions or classes, providing the stream reader and stream writer interface respectively. Error handling is done in the same way as defined for stream readers and writers. The stream reader writer instances define the combined interfaces of stream reader and stream writer classes. They inherit all other methods and attributes from the underlying stream. The stream decoder. The stream decoder translates data from one encoding to another, which is sometimes useful when dealing with different encoding environments. The design is such that one can use the factory functions returned by the lookup function to construct an instance. So stream decoder takes stream, encode, decode, reader, writer, and others. It creates a stream recorder instance which implements a two-way conversion, encode and decode work on the front end. The data visible to code following read and write, while reader and writer work on the backend, the data and stream. You can use these objects to do transparent encodings, example from Latin 1 to UTF-8 and back. The stream argument must be a file-like object. The encode and decode argument must adhere to codec interface. Reader and writer must be factory functions or classes providing objects of the stream reader and stream writer interface respectively. Error handling is done in the same way defined for stream readers and writers. Stream recorder instances define the combined interfaces of stream reader and stream writer classes. They inherit all other methods and attributes from the underlying stream. Encodings and Unicode. Strings are stored internally as sequences of code point in range U0 to 10 FF. So you can look at tab 393 if you want to know more about it. Once a string object is used outside of CPU and memory, NDNS and how these arrays are stored as bytes become an issue. As with other codecs, serializing the string into sequence of bytes is known as encoding, and recreating the string from the sequence of bytes is known as decoding. There are a variety of different text serialization codecs which are collectively referred to as text encodings. Simplest text encoding called Latin 1 or ISO 88591 maps the code point 0 to 255 to the bytes 0x0 to 0xFF, which means that a string object that contains code points above 00FF can't be encoded with this codec. Doing so will raise Unicode encoder error that looks like following. So you can read this. There is another group of encodings that choose a different subset of all Unicode code points and how these code points are mapped to the bytes 0x0, 0xFF. To see how this is done, simply open encoding /cp1255 12525.5, which is an encoding that is primarily used on Windows. There is a string constant and 256 characters that show you which character is mapped to which byte value. All of these encodings can only encode 256 out of this is 1,114,912 code points defined in Unicode. Simple and straightforward way that can store each Unicode code point is to store code points as our 4 consecutive bytes. There are 2 possibilities: store the bytes in Big Indian or Little Indian order. These 2 encodings are called UTF-32 and UTF-32BE and early respectively. There is Big Indian and Little Indian. The disadvantage is that, for example, if you use UTF-32 Big Indian on a Little Indian machine, you will always have to swap bytes on encoding and decoding. Python's UTF-16 and 32 codecs avoid this problem by using platform's native byte order when no BOM is present. Python follows prevailing platform practice, so native Indian data round trips without redundant byte swapping. Even though the Unicode stands default to Big Indian when the byte order is unspecified. When these bytes are read by a CPU with a different Indianness, the bytes have to be swapped. To be able to detect the Indianness of UTF-16 or UTF-32 byte sequence, a byte order mark is used. This is the Unicode character UFEFF. This character can be appended to every UTF-16-32 byte sequence. The byte swapped version of this character 0xFFFE is an illegal character that may not appear in a Unicode text. When the first character of UTF-16 UTF-32 byte sequence is FFFE, the bytes have to be swapped on decoding. Unfortunately, the character FFFE FF has a second purpose as a 0 width, no break space. A character that has no width and doesn't allow a word to be split, it can, example, be used to give hints to the ligature windows up. The Unicode 4 using FEFF as a 0 width, no break space has been deprecated, with U2060 word joiner assuming resolved. Nevertheless, Unicode software must be able to handle FEFF in both roles. As a byte order mark, it is a device to determine the storing layout of the encoded bytes and vanishes once the byte sequence has been decoded into a string. As a 0 width, no break space, it's a normal character that will be decoded like any other. There is another encoding that is able to encode the full range of Unicode characters, UTF-8. UTF-8 is an 8-bit encoding, which means there are no issues with byte order in UTF-8. Each byte in a UTF-8 byte sequence consists of two parts: marker bits, or the most significant bits, and payload bits. The marker bits are a sequence of 0 to 4, 1 bits followed by 0 bit. Unicode characters are encoded like this, with X being payload bits, which when concatenated give the Unicode characters. So starting from Unicode 0 to 7F, you have 1, 2, 3, 4, and 7 XLs. So these are the payload bits. Then from 80 to 7FF, so you can read this table for yourself. The least significant bit of Unicode character is the rightmost bit, X bit. As UTF-8 is an 8-bit encoding with no byte order mark is required, and any U plus FEFF character in the decoded string, even if it's the first character, is treated as 0 with no break space. Without external information, it is impossible to reliably determine which encoding was used for encoding the string. Each char map encoding can decode any random byte sequence. However, that is not possible with UTF-8. As UTF-8 byte sequences have a structure that does not allow arbitrary byte sequences. To increase the reliability with which UTF-8 encoding can be detected, Microsoft invented a variant of UTF-8 that Python calls UTF-8 SIG for its notepad program. Before any of the Unicode characters is written to the file, a UTF-8 encoded byte order mark, which looks like this as a byte sequence 0xCF, 0xBD, 0xDF is written. As it is rather improbable that any char map encoded file starts with these byte values, which would, example, map to Latin small character I with parenthesis, right floating, right pointing double angle quotation mark, inverted question mark, and ISO 88591. This increases the popularity of UTF-8 SIG encoding can be correctly guessed from the byte sequence. So here the byte order mark is not used to be able to determine the byte order used for generating the byte sequence, but as a signature that helps in guessing the encoding. On encoding, the UTF-8 SIG codec will write these 3 bytes to the file. On decoding, UTF-8 SIG will skip those 3 bytes if they appear as the first 3 bytes in the file. In UTF-8, the use of byte order mark is discouraged and should generally be avoided. Then we have standard encodings. Python comes with a number of codecs built in, either implemented as C functions or with dictionaries or mapping tables. The following table lists the codecs by name together with the common aliases and the languages for which the encoding is likely used. Neither the list of aliases nor the list of languages is meant to be exhaustive. Notice that spelling alternatives that only differ in case or use a hyphen instead of an underscore are also valid aliases because they are equivalent when normalized by normalized encoding. For example, UTF-8 is a valid alias for UTF-8 codec. On Windows, CPXXX codecs are available for all code pages, but only codecs listed in the following tables are guaranteed to exist on other platforms. See Python implementation detail. Some common encodings can bypass the codecs without machinery to improve performance. These optimization opportunities are only recognized by CPython for a limited set of aliases. UTF-8, Latin 1, and so on. Minus is removed, and we can read that. So many of the characters that support the same language, they vary in individual characters. Example, whether the euro sign is supported or not. And in the assignment of characters to code positions for the European languages in particular, the following variants typically exist. An ISO 8859 code set, a Microsoft Windows code page, which is typically derived from an 8859 code set, but replaces control characters with additional graphic characters. An IBM EBC DIC code page, an IBM PC code page, which is ASCII compatible. So it's a table where we have codecs, aliases, and languages, which you can read on your own if you want to know all the details. Then we have Python specific encoding. A number of predefined codecs are specific to Python, so their codec names have no meaning outside Python. These are listed below in the tables based on the expected output and expected input and output types. Note that while text encodings are most common use for codecs, Down the line, codec infrastructure supports arbitrary data transforms rather than just text encodings. For asymmetric codecs, the standard meaning describes the encoding detection. So we have following codecs for string to byte encoding, and then we have for bytes to bytes. Then we have standalone codec functions. The following functions provide encoding and decoding functionality similar to codecs, but are not available as named codecs through codecs.encode or codecs.decode. They are used internally, for example, by Pickle, and behave similarly to string escape codec that was removed in Python 3. We have escape underscore encode, which takes an input and error says none. Encode input using escape sequences, similar to how rep from bytes produce escape byte values. Input must be a byte subject, returns a tuple output and length, which output is a byte, where output is a byte object and length is number of bytes consumed. Then we have escape underscore decode, which is the reverse of encode, and it converts escape sequences to original bytes. Then we have text transform. The following codec provides a text transform str to str mapping. It is not supported by encode, which only produces bytes output. Then we have encoding package. This module implements the following function. One is normalizing encoding, which we already seen. Normalization works as follows. All non-numeric alphanumeric characters except the dot used for Python package frames are collapsed and replaced with a single underscore. Leading and trailing underscores are removed. For example, this space minus semicolon hash becomes underscore. Note that encoding should be SVM only. Then we have search function, search for the codec module corresponding to the given encoding, named encoding. The function first normalizes the encoding using normalized encoding, then looks for corresponding alias. It attempts to import a codec module from the encoding package using either the alias or the normalized names. If the module is found and defines a valid get re-entry function that returns a codec info object, the codec is cached and returned. If the codec module defines a get aliases function, any return aliases are registered for future use. Then we have Win32 code page search function, which searches for a Windows code page encoding of the form cpxxxx. Then we have encodings.idna, internationalized domain names in applications. This module implements IFC 3490, that is internationalized domain names in application, and IFC 3492, a string type profile for internationalized domain names. It's built upon the Punycode encoding and string type. If you need the IDNA 2008 standard from RFC 5891 and RFC 5895, use the third-party IDNA module. These RFCs together define a protocol to support non-ASCII characters in domain names. A domain name containing non-ASCII characters such as www.alliance.nu is converted into ASCII compatible encoding, such as www.xn-alliance npd.nu. The ACE form of the domain name is then used in all places where arbitrary characters are not allowed by the protocol, such as DNS queries, HTTP host fields, and so on. This conversion is carried out in the application if possible and visible to the user. The application should transparently convert Unicode domain labels to IDNA on the wire and convert back ACE labels to Unicode before presenting them to the user. Python supports this conversion in several ways. The IDNA codec performs conversion between Unicode and ACE, separating an input string into labels based on the separator characters defined in section 3.1 of RFC 3490, and converting each label to ACE as required. And conversely, separating an input byte into labels based on the dot separator and converting any ACE label found in the Unicode. Furthermore, the socket module transparently converts Unicode hostnames to ACE so that applications need not be concerned about converting hostnames themselves when they pass them to socket module. On top of that, modules that have hostname as function parameters such as http.client and httplib accept Unicode hostnames http.client then also transparently sends an ID and a host name in the host field if it sends that field at all. When receiving host names from the wire, such as in reverse name lookup, no automatic conversion to Unicode is performed. Application wishing to present such host names to the user should decode them to Unicode. The module encodings.idna also implements the name prep procedure, which performs certain normalization on host names to achieve case insensitivity of international domain names and to unfamiliar to unify similar characters. The name prep functions can be used directly if desired. So we have encodings.idna.nameprep, which takes a label, return the name prep version of the label. The implementation currently assumes query strings, so allow unassigned is true. Then we have to ASCII, convert a label to ASCII, use std3a ASCII rules. If 3 ASCII rules is assumed to be false, then we have to Unicode. Then we have encodings.mdcs Windows NC package. This module implements the NC code page and available only in Windows. Then we have encodings.utf8_sig, UTF-8 codec with bomb signature, which we have already seen. This module implements a variant of the UTF-8 codec. On encoding, a UTF-8 encoded bomb will be appended to the UTF-8 encoded bytes. For the stateful encoder, this is only done once. On the first byte to the byte stream on decoding, an optional UTF-8 encoded byte out of mark at the start of data will be skipped. So with this, we end the read-through of Codecs. As I said in the previous video, these are not very commonly used. Okay, they have their uses, but it's not very common. So it was the boring part which we went through. And now from the next video, we will have interesting stuff. And let's see when this thing becomes boring again. Okay? Because eventually there will be something which will become boring. So we'll see. Okay? By the way, we are not going to cover the graphical user interface. We will not. Okay? We will skip that part. And we might skip multimedia services as well. But we'll read multimedia services. We will skip TK for sure. I don't want to go into GUI with TK. If you want to do GUI, there are much better libraries like PyGTK or PyQt is available. So I think we will have lots of good stuff coming, useful stuff, and the documentation will be less boring for these modules. So in the next video, we will go through the data type, and we'll see how we can use date time. And I'll bring plenty of examples for this. Okay. So I hope that you did not get bored with the boring theory of Codecs module and stuck. Before that, it was quite good. But I would understand if we get bored. So let's meet in the next video to discuss date time. I thank you for watching the video and enduring the torture which I called on you. Thanks a lot for watching the video. Enjoy.